Concurrency is hard. I'm going to start with that. And part of the reason why it's hard is because of mutation, right? You have to figure out how you're going to control mutation. The other part is about efficiency. And so if you were just concerned about mutation, you could say, well, we'll write everything in Haskell, and you can throw a compiler switch, and it will speed up your application on my 20-core machine by about 15% if you're lucky, okay? And that's because you're relying on optimization, but you really need to be able to express the concurrency. So how do we do that? A lot of years ago now, I was involved in a project to bring up Lightroom, which is a professional photo editing package that Adobe produces. And we wanted to get Lightroom running inside the browser. And this was before there was WASM, and so there was asm.js. And asm.js is a single-threaded environment. And Lightroom is a multi-threaded professional application. And so the challenge became, how do I take this multi-threaded thing and get it running on a single thread and still be efficient and usable and interactive? And also, I didn't want to have to fork the code, right? So whatever changes I made within the code, I wanted to scale back to run on desktop and make full utilization of however many cores you have. So that was the challenge. And we're not going to talk about everything I did to solve this, but we're going to focus on this idea of futures and continuations, because that's a fairly fundamental building block. And my first thought when I set out to do this was, well, there's boost futures, and they have continuations, and they're already out there. The standard library futures don't have continuations. So I'll just pick up boost futures, and I'll build this. And I wrote this little test function as kind of my first thing. All it does is it makes a future of 42, and then it says when that's resolved, which it is from the start, get the value out of it and add to. But then also forking in a different direction, get the value and add 3, and then print both those numbers. And the red highlighted is where the program crashes. Okay? The reason why it crashes is boost futures with continuations effectively have move semantics, but they're not declared as move only. And then is a consuming operation. So it consumed F. So down here where I was moving F, that's a use after move right there. And now when I try to call .then on basically a null object, I'm toast. But split was a very important operation. And I could figure out how to implement split with boost futures using a bunch of trickery, but it had two problems. One is, even though I knew how to do it, people are going to write this, and their code's going to crash. And the other problem is I couldn't figure out how to do it efficiently. Okay, so what's the problem? So let's describe what I'm trying to do. This is a consumer product I worked on years ago, no longer in the market. This was called Adobe Revel, and this is an image of it running on an iPad. But it's the same rendering engine as our professional Lightroom product. And so what I want is a very fluid interactive behavior in this application with arbitrarily large images and arbitrarily complex pipelines of computation. It's a non-destructive imaging model. So every time you're sliding something like an exposure slider, it's actually touching about 8 stages in a 40-some odd stage pipeline and re-rendering everything live. So how do you get the smooth interactive feel? Well, what you do is conceptually in the background of this is you create a single GPU texture that represents the entire image at a low resolution. And that way, if you're panning or zooming, you're never going to see black. You'll see something blurry. And then if you come along and you edit some sliders here, maybe we crank the vibrance way down, then what happens while you're moving that slider is we do a fast preliminary render, sometimes at a low resolution, sometimes it actually is at a high resolution, but it's a delta from a previous high resolution image, so that we can do that very quickly. And then as your finger slows down, we can afford a little more time and a slower frame rate, and so then we'll do a higher resolution version of the image or a higher quality version. And then we'll finally fill in the frame about when your finger stops. But we're doing this dynamically. So if you start moving your finger again in the middle, it'll drop resolution and try to keep a high frame rate the whole time. So this is very much a latency problem, right? How do you keep a very high latency to keep a very high frame rate to make it very seamless and interactive, and you're willing to sacrifice quality to maintain that? And then when we're done rendering your foreground image there, what you're actually looking at on the iPad, we'll go ahead and we'll render the whole image and then downsample it to a small resolution. So now if we pan or zoom, you're not going to see black, you're going to see the actual pixels, and you're not going to see stale pixels. Okay? So if you pan up, something like that, then logically what we're doing is we're moving the iPad, not the image, and then we'll try to chase that animation and render that final frame. So by the time the motion stops, because you have a little bit of animation going on there, anytime you're panning, you'll see quality pixels. So the effect is really surprising. Even at a relatively low frame rate, like 10 to 15 frames per second for what you can actually render a quality image at, you can drive the device at full frame rate. And on an iPad Pro, that's 120 frames a second. Okay, so it feels very good. So how is all of this done? Well, we've got this state machine going on that's driving the various things. You don't want to get stuck where you've only got a preview image on the display. So this is always going to keep looping back until we've got a quality foreground image. But each one of these stages is queued off asynchronously because we're trying to get back to the event loop so we can fetch the next event. And drawing from the event loop helps us make our decision about where we're going to next, as well as we're timing the frames inside of this coroutine. But if we're in the middle, say, of rendering a background, which is a very expensive operation because we need all the pixels in the entire image, and you slide your slider, we need to cancel that operation so that we can get around here and over to get a preview on the screen very quickly, okay? And that means we need all your cores back so that we can get this frame now. And if this thing is taking 1/5 of a second, and we have to wait for it to complete, or we serialize our cancellation across the cores, then that low quality frame isn't going to appear for 1/5 of a second, and you get heavy lag in the application, and it doesn't feel right. Okay? So it's not just how efficiently we can get throughput in the system, it's part of how we can get low latency is how efficiently can we cancel within this system. So futures and continuations provide a nice mental model for how to take a serial application and turn it into an asynchronous application. But they also provide a nice model for how you can take an existing asynchronous application and kind of clean it up into something that's a little easier to reason about and bring it down to the point where you can run it in a single threaded environment. So conceptually, what futures with continuations are is you take a function, some task, some operation, and you turn it into a function returning void. And the future, the box here, is some token for your result that's carrying what the final result was. And at some point later now, you can retrieve that result. And you can start to chain these things together. So you can add a continuation to a future and get another future out and keep going. Conceptually, all that this is I'm composing functions. I'm doing g of f of x. When I call it, it'll look something like this. I'll say, oh, I've got a future, which is a result of pushing function f, making that async with the argument x, and then piping the result into g. Okay. Now, if you can split your futures and you can have a win all, so you can start to join them, what you end up starting to build is a dependency graph that's carried by each of the futures. Okay? And because in any of these operations can be bound to a future, right? You can have a lambda, you could capture a future in your reference. The dependency is carried throughout the whole graph. Okay? And when you're sliding that slider, and we're doing operations and we're canceling operations, and some of those operations are deltas from some other operations, and some of those operations required a cache, and the next operation requires the same cache, so we don't want to blow that cache away, we get a very complicated graph like this of operations, and then we decide, cancel the background image. What is the background image? Okay. There's no way that I can say, throw some Boolean flag and have everything read the Boolean flag, because maybe this is my background image, and this is the preview image I'm trying to get to next. And they have shared dependencies. Okay. So what you want to be able to do is say, no, I'm done with my background image, just destruct the future for that, let it go. And that's going to take the operation that was leading to it with it, and then it's going to take any futures that that thing was bound against with it, and what we're left with is the chain of computation that we're leading to. So literally, if you're using Lightroom Mobile, which is the same engine now today, you're sliding your slider across there, we are building these graphs and doing cancellation probably 30 to 40 times a second. Okay. So how do we define efficient cancellation? Well, we've got a dependency graph, which is a bipartite, which just means we have two types of nodes. We have futures and we have operations. And you can't connect a future to a future. You have to go through an operation. And you can't connect an operation to an operation. You have to go through a future. So that's what a bipartite graph is. Okay? So of operations and their results are futures. Operations may be scheduled for execution. They could be active, right? So they could be scheduled, queued up somewhere. They could be active, which means they're currently executing, or they could be in a completed state. They're already done. If a result is no longer needed, the future is destructed, then any uniquely contributing operations are canceled. Uniquely is a key point here, right? We don't want to cancel other things. Active operations receive a stop request, which means it's a voluntary please stop, and scheduled operations will not start, and their resources, which may include the results of other operations, are released. And you want that to happen immediately because those things could be holding on to other asynchronous operations. So cancellation is efficient if every active uniquely contributing operation immediately receives a stop request and no scheduled operations start after the cancellation. Okay. The other thing we need in this environment is for it to be wait-free. Why do we need it to be wait-free? Well, on a single-threaded system, remember we're targeting ASM.js as part of the thing here. Tasks are queued to the main run loop, which means that if I wait for a task that I just queued to the main run loop, I'm going to be waiting a long time. I'm on one thread. It's an immediate deadlock. This allows work to be interleaved with responding events, to respond to events. The amount of work done by each task needs to be small enough, a small grain size, to not block user events coming through and being responded to, right? So even though I've got an operation that's going to take a significant amount of time, I don't want that blocking my slider, even if I'm on a single-threaded system, which means I need to take that piece of code and transform it into chunks that will let me cancel it at any point. And waiting for a task to complete, a synchronous wait or a sync wait is a deadlock in a single-threaded system. In a multi-threaded system, a sync wait is also very bad. So how bad? Well, one of the reasons why it's bad is Amdahl's law. Okay? Amdahl's law is measuring how much performance we get for how many cores if some percentage of our application is synchronized. Now, you're never going to get this straight red line. This is perfect. This linear scale here goes up to 16x performance and 16 processors. You're never going to hit that red line. And the reason why you're never going to hit that red line is because resources on the machine itself are shared, right? Your memory is shared. Your caches are shared. There's some amount of synchronization happening at the processor level that's going to start to bend that curve, even if your work is as independent as you can possibly make it. But if you look here, if just 10% of your application is synchronized, then at 16 cores, you only get a little more than a 6x performance increase. Just 10%. And no matter how many cores you have, you will never exceed 10x performance increase. Okay? So we don't want to be waiting. We don't want to stop a thread. Now, the other reason is stopping threads causes deadlocks. Here's a single-threaded system. We have a task, we queue the task, and then we wait for the task, and we're deadlocked. We're stuck. Thank you, Nick. Refrigerator deadlocked. So you say, well, what happens if you have two threads? Now, this thread queues a task and stops and waits for it. And then that task queues a task and stops and waits for it. And now you're deadlocked. Okay. So in a fixed size thread pool, if you have sync waits, which is what this is called, a synchronous wait waiting for the operation, you will eventually see a deadlock. In fact, when I started working on this, I fixed a whole bunch of deadlocks in the Lightroom engine because I had to get everything running on one core machine. And guess what? We had these bugs that were incredibly difficult to reproduce on many core machines where things deadlocked that I also fixed. Okay? So the more cores you have, the probability that you hit this pattern starts to decrease because you have a thread available that can steal a task and get things unstuck. But a good way to deadlock a machine in a fixed size thread pool is to say, oh, I've got some piece of work. I'm going to fan it out for all the cores that I have, and then I'm going to wait for the result, and all of those tasks do the same thing. Pretty much a guaranteed deadlock. So don't do that. So if you're building thread pools, you can say, well, if I can detect when I'm stuck, I can add another thread to my thread pool. Okay? Well, if you're doing this, that's going to lead to a thread explosion. Okay? So you'll start adding threads and adding threads and adding threads and blocking and blocking and blocking and blocking and blocking. And pretty soon you're just going to exhaust the resources on your machine. So who's familiar with Intel TBB as a concurrency model? So thread building blocks from Intel. Arch Robinson, who did the design for that, was very fond of saying, if you can't run on a single threaded environment, you can't run on a multi-threaded environment. It's just that simple. So I wrote this little library to solve all of these problems in Lightroom. And I gave a talk. It's Better Code Concurrency talk. You can look it up. And I cleaned up my code, and I packaged it as a little library on GitHub. It's the STLab libraries, concurrency libraries. It was written almost entirely at the hotel bar at C++ Now. Felix Petroconi, who now runs the ACCU conference, he found my library useful and started contributing code. And now, to my own surprise, the library is in broad use at Adobe and other companies. It's actually not in Lightroom that I'm aware of, other than some preliminary piece of it. But it's come full circle. So we solved all these problems, right? And splits work great in STLab. You can just say, oh, pipe F to G and pipe F to H and get two futures out of it, and they work as you would expect. So what's the problem with this solution? Well, every time we have that pipe operator and we attach a continuation, what do we have to do? That implies shared memory, so we've got a small object allocation and deallocation. This is a chart of the cost of operations. So we are all the way down here at 2 to 500 cycles for that operation. Okay, this is on a logarithmic scale, so that's not great. Okay, we also have to do some synchronization. That's going to cost us 15 to 30 cycles each time we have some atomic op. Okay, so our continuations require share state, memory allocation, deallocation with atomic operations to control the lifetime of that shared state, plus attaching a continuation requires some synchronization, so we've got an atomic operation for that, plus resolving the continuation requires synchronization, and all of this is under the hood of this simple little pipe operator. Okay. So the end result is that pipe operator is 100 to 1,000 times the cost of just a function call. Right? That's painful. And if you know the continuation in advance, you don't want to pay that cost. If I know that this F is going straight to that G, I don't want to do it. The only time I want to do this is when I'm dynamically like responding to some user events. Then it's okay to say, okay, at this point, this thing's already in flight. I will pay those synchronization costs and attach the next operation. But if I know this is always just going here, it's not in response to an event, I don't want to ever write that. Instead, what I want to do is I want to say, oh, don't make F async and then pipe it to G, do async a composition of G and F. Okay, so remember we said that all that this means is this is G of F of X. So this is G of F of X.
Does that make it harder to cancel it and cancel G if F is started on it?
Yeah, so you're going to be canceling both of these as one piece of work. So if you do have significant size pieces of work, then you would want to split them. It's going to depend on your grain size. Okay, so, but if you do that, then if I've got some operation, whatever I do, and it's returning some future, and I don't want to have to pipe on it when I know where it's going to next, I have to change the operation to take the continuation as an argument, and that's a templated thing because it's going to return whatever it wants to return. It's a mutation. And then that's going to return some future of whatever the result of that composition is. And then I've got to do my async and compose, and so on and so on and so on as you build up your application. And now your application looks really weird. Every function that you call, you're handing it a function, and you're confusing yourself, right? I've never seen anybody do this right at scale. Okay, I've seen people try and just make a mess. So senders receivers proposed for the next C++ standard for 26. This is the problem that they set out to solve. Okay, so when you write then F, then G, logically what that is compose GF. Okay, it's just a function composition. That's all it is. Okay. And if I say transfer, which lets you schedule work on some other thread, pipe to then F, some function F, this is really bind this, whatever comes after it, F, to my scheduler. Okay. Now, bind and compose are returning functions. They're not actually doing the thing. And because they're returning functions and not actually doing the thing, I don't need any synchronization here. So I'm building up a program that describes my asynchronous behavior, and then at some point later, I'm going to call start on that and invoke it, and it will run. And I can do all of this composition in bind front flat without a heap allocation. This is just creating a bigger and bigger and bigger type, okay, that holds all the information. And if I say transfer S to then F to then G, this becomes bind front S to compose G of F. Okay. So that's the basics of how senders receivers work. But senders receivers are also very complicated. I was having a conversation with Eric Niebler, and I said, I referred to this as a sender receiver because it's both a sender and a receiver. And Eric said, well, std_exec doesn't have a thing that's a sender receiver. And I said, well, what do you call a pipe thing, something that you can pipe something to that can also be piped to the next thing? And he's like, we don't really have that. And I'm like, yes, you do. What is then? What is then F? And what he came back and told me is he said then F is a sender adapter closure. Okay? So this is a sender adapter closure. But that's not how senders receivers are written. They have complicated APIs feeding into them. And this is an argument I've been having with Eric for almost 10 years. I've been saying, look, you're solving this problem, but it's a very complicated solution. And at the end of the day, all you're doing is function composition. And he's like, no, we're not. We're doing other stuff. I'm like, no, you're not. You're just doing function composition. That's all you're doing. Okay, and this is where we actually get to start about talking about chains. So let's start flat. F pipe to G, pipe to H. The desired result of this is that we have compose H, compose G, compose F. Okay, we want to just compose those things together. But we want to do it without nesting so we don't blow out the stack. So we don't actually want compose, 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 compose. Okay, and we want to be able to keep building this up more and more and more. Okay. So what do? Well, links are just functions which are stored in a tuple. Actually, it's just a tuple of functions. Okay, so I just have a tuple of functions and I build this all up. And then I've got a way that I can take a fold expression and expand that tuple at execution time and execute it flat and rely on the compiler to reuse all the intermediate variables that are going, because this returns a result and this has to pick it up. Senders receivers does the same thing. They call it trampolining to keep from blowing out the stack. But if you look at it, it's not done with fold expressions. It's a very complicated piece of code, and they're manually allocating space on the stack for the result type, and then picking that up and using it, and then reusing the same hole, doing a launder and recasting and all of that kind of stuff to reuse the same memory. I'm like, I let the compiler do that. Okay. So, question for you guys. If I've got this composition, F to G to H, what if an error happens when I actually invoke it? Okay, what happens? Well, if we were to just execute that composition, H, G, F of X, and F throws an exception, can G or H catch it? Right? They can't. Okay, if I wrote this piece of code and F throws an exception, G and H never get a crack at it. And people tell me, well, they would if you wrote it with stood expected, but that's not how you'd write that with stood expected. You'd expand it into this. You would say f.x.and then g.and then h, so that you're not burdening all of these things with taking a stood expected. Okay? So error handling sits outside of these links. So I don't have to burden the interface on these things with what happens when there's an error. And that brings us to segments. So what's a segment? Well, in my terminology, when I say on S, it creates a segment, which is a function that is the applicator function. Okay, so S is my applicator function, S, bound to the subsequent sequence of functions, right? Remember I showed transfer onto a scheduler, transfer S? Okay, this is the same thing. This is bind front of S of F pipe to G. Okay, so additional functions can still be appended onto the end. We can keep piping, and we can pipe on another segment onto the end. Just start a new segment. S determines the context in which F and G are executed, right? F and G are passed as arguments to S. So kind of all the magic about where do you want this piece of work scheduled on a thread, on a GPU, all of that, that's S's responsibility. And we don't have a whole bunch of things. We just have on S. And then you pass in what you want as the argument. So logically, it looks like this, right? Now we've got our applicator function, and we've got F, and we've got G, and we just store this flat. We do a struct that this is an applicator, and this is a tuple of functions. And it's just flat, sitting in memory. This is a very simple data structure. So that's a segment. Okay, so segments, because they're executing all of the functions that are passed to them, this is where you can start to do things around exception or error handling or things of that nature. Okay, so if I wrote, I'll call this thing my expector, all my expector does is it executes whatever my function is with whatever arguments I pass to it, and then it returns the current exception. Okay, if it catches, if it throws. And then I wrote this badd, it's my bad add function, which throws a runtime error if x equals 42. And then I can write this. I can say on expector, do my bad add, and then pipe the result of my bad add to this lambda expression that returns x times 2. And if I feed it 12 times 5, I'll get an expected 34. And if I were to plug in 42 here as my x, I would get expected holding my runtime error back out. Okay, so my segments are where I start to provide the environment within which my functions are executed. And that brings us to chains. Okay, a chain is simply a sequence of segments. Right? On F, on S, pipe to F, pipe to G, on T, pipe to H. Segments are linked. The next segment is part of the prior segment. Okay, those things are logically tied together. So this becomes, we've wrote it out as a lambda expression, right? We're taking F pipe to G piped to on T, pipe to H, storing that in SF, and then S is our scheduler, and then it takes whatever arguments it takes, and it returns S applied to the stored function and the args. I thought I had cleaned up this example, but apparently not. So this is also just stored flat. This is now effectively a tuple of tuples. Okay, a tuple of functions. The whole chain is built like that with all the applicators. And so on S, this is binding F and G to that. This is binding H to that. This is binding I, J, X. And I can keep appending. If I append more just functions, they go here. If I append more segments, it starts a new one, and it goes there. And this is just a 2D data structure, and I can build it out as much as I want. I haven't found one yet. So this has been a problem with sender receivers. I think my type information is less than theirs. They pull tricks to start to hide the type information. It turns out if you have a lambda and you capture something in the closure, then the type information from the capture in the lambda is kind of erased from the outside. So they pull some interesting tricks like that. So far, I haven't had to pull those tricks. Maybe I will need to. But in any case, this shows how when you have a chain of operations, how these things all link together. Okay, so conceptually, this is one function, which is a composition of F and G and H and I and J and K. Okay, so this is K of J of I of H of G of F of X is the composition we just built up here by doing the appending. And these things are controlling where the things after them are executed. Okay, in what environment. Otherwise, they're kind of transparent to the function. Right, so what does all of this have to do with async? Right, well, a chain is a program that describes this sequence of execution, and we can create segments that provide an execution context to schedule the segment. Functions on chains can append a promise and start the chain, returning a future, right? So if I want to get this thing started and I want a future out the result, kind of all that I need to do is stick a function on the very end of my chain that takes the result, sends it to a promise, and the whole thing returns a future. And it can bind additional arguments to every applicator, i.e. a stop token and a set exception, right? Remember, all of this is stored flat, so the compiler has all the type information. So you can write algorithms to transform this structure. So when you get a chain and you say, oh, I'm going to execute this chain, we can inject a path for our exception to go straight to our promise at the end. We can inject code that says, if there's been a stop request, just go to the end, okay? So we can do that. All that's doing is that's going through our list for each of our segments, and we're wrapping that segment. We're binding that segment with something that's got a stop token and a set exception call to all of those operations, and then we just invoke the operation, right? So otherwise it's transparent. So we can wrap everything, and we can build the complete system. And then when we go to execute this, this gets appended onto this, and it forms that whole big chain. And now we have all of our asynchronous code executing. So chains are a general purpose. How general purpose? This is an open issue. I have a conjecture, which is given an SK combinator. This is for Connor over here. I don't know who If people in this room know what an S and K combinators are just functions that take functions and return functions. And there's a well-known result, which is that if you just have SK combinators and you can combine them as functions in arbitrary ways, then it creates a Turing-complete system. And you can win $20,000 if you can prove that you can only do it with an S combinator. That's Stephen Wolfram has a challenge out for that. But can I do SK combinators in here? Well, one interesting thing is the S combinator. S combinator is something that takes 3 arguments and x, y, z, and what it returns is x of z. X is a binary operation. X of z and y of z. Okay, and z appears twice, and that's a split. Okay, so splits. Well, can I do splits? They're not that easy, right? I can do a logical split within the system. I can kind of, within a function, I can fan out and bring things back together. That's fine. But what I want is this split that I was showing you in Lightroom, where I'm holding on to some result over here, and I'm holding on to some result over there, and those are not in the same chain, in the same function. They're logically distinct. They've been split out, right? So what does it mean to split? Well, synchronization is required, okay, because we have 2 paths with 1 common root of computation. The shared portion should only be executed once. That probably means that canceling should only cancel the non-shared portion, right? We don't want it broken cancel. And I can't see a way for this to have any arguments because I can't start one fork with 42 and another fork with 5 and only execute the shared portion once. What does that mean, right? Those values start at the shared portion and feed in, okay? So it has to be fully bound. So I have to bind all the arguments up front. And then the first invocation, one of these leaf nodes should get it started, and the subsequent invocations should be ignored, right? So I can start it from either side and get going. Senders receivers has a split algorithm, okay? And part of what prompted this whole talk was I went to use it, and I did my split, and I had my 2 things, and I dropped one of them, which is cancel, and it canceled my other one. And my canonical example here is if I have a document that I'm working on, and I split it, and I say, go save that instance of it, okay? And now go do more edits. Oh, wait, I didn't mean to save it. Cancel the save. I really, really, really don't want that to cancel all my other edits, okay? Those 2 things need to be independent. And so there's a long thread on the Discord for senders receivers, and Eric Niebler suggested that maybe I could dig in and figure out how to fix this issue. And the implementation of split that's existing in senders receivers is 400 lines of very dense code. And I'm sorry, it would take me too long to figure out Eric's code. But maybe I can nerd snipe somebody else into fixing this. Okay. So next steps. Well, chains can't currently do anything that senders and receivers can't do. I haven't implemented split on chains yet. But the model is simpler. And there's an asterisk there because I don't know that. I have some differences on how things are bound lately. And all of my data is flat, which means there are transformations that I might be able to do on mine that you can't do with senders receivers. I've got a little chain library, but it's a prototype, very prototype library. It's like all in one file, just, like main. Here's the implementation. So it's a prototype. It's missing production features. I haven't pulled through, like, what if one of these functions has a void type, and how do you carry that through the system? And big argument for regular void there, because dealing with void in templates is just a pain in the rear. I haven't worked through all the places where I could minimize copies, right? I'm building these structures dynamically, and I'm not really paying attention to how many intermediate copies of the structures I'm building. I haven't gone through and made sure I'm handling perfect forward and move only types everywhere where they need to go. I'm not handling copy everywhere where copy is appropriate, which is a similar thing. So there's a lot to do, right? If it's like I said, it's less than 2 weeks old. So that's it. So that's my draft of a talk for the draft of a library for a half an idea. Thanks. And that slide's got a QR code that you guys have no idea where that goes to.
It's to donate, if you want to donate. And if you want to ask a question, I can give you this. Anyone have questions or comments? Yeah. That's fair.
So. It is on GitHub. Yeah, it's on GitHub under stlab/chains. It's not pretty. You know, it's a difficult thing, right? Senders Receivers has a 10-year head start on me, and it's been looked at by a number of amazing people who are very talented. And honestly, this is not intended as a shot across their bow or anything. This was partially done for me to try to understand how senders receivers work and how I can use them and where they don't work. And one way to do that is to try to understand what it is at its core and re-implement it and see where that takes you. And I'm not 100% convinced that by the time I'm done, I'm not just recreating all the complexity that they've put into senders receivers. Already, I think on the Discord, this has had an impact on the sender receiver's design, especially around split. Like I said, their split is broken. And so now there's a long discussion on what split should do and what does it mean. And it's a difficult thing because you want this function composition to behave as if it were the result of the function, but it's not. It's a function, and that's fundamentally a different thing. I have some other complaints around senders receivers, like, you know, futures are just senders, and it's really unclear when you have a future or what the type of the future actually is in the library, and so there's some weird things around that. But like I said, you know, it's been looked at by a lot of smart people over a lot of years, and I've been just throwing hand grenades at them occasionally. So I don't know. I think if I were to derail senders receivers with this work would probably not be ready for C++ 26, and that would make me very sad. We would have nothing, and we would go forward. So that absolutely is not my intention. I want senders receivers, despite their complexity. Okay, they fix a real problem, which we kind of saw. That's what they're intended to fix. Their API is complicated. Okay, so is C++. So that's my thought. But maybe people looking at this will steal some ideas and maybe simplify sender receivers, or maybe find a way that they can clean up the proposal a little bit, and maybe it doesn't have to be so complicated, right? Right. If you look, like, senders receivers has complicated customization points and things like that, and all of my magic happens on just transformations of an object, and so I don't need, you know, all of this extra machinery around it. At least I don't think I do. I haven't implemented everything yet.
Can you go back to the slide where you define efficient cancellation? I got a question about that.
Where I define efficient cancellation?
Yeah, it was early on.
Yeah. We'll find it here. Yep. Wait, free. Yeah. There you
go. Okay, so you say cancellation is efficient if every actively uniquely contributing operation immediately receives a stop request and no scheduled operations start after the cancellation.
Yeah.
So those are two, like, timing constraints, and we're talking about a concurrent context here. So are you talking about are those like timing constraints relative to the thread that cancels? Because what does start mean in a concurrent system?
Right. Well, when I'm talking about efficiency first, what I'm talking about is an idealized thing. Okay. So when you talk about is an operation efficient, if it's efficient, it means there is no possible way to implement it faster. So you can view this as being the upper bounds of efficiency may not be achievable.
Yeah.
Okay, so like all the things you say, it's like, yeah, it actually, from the point when I drop the future, it takes time to do the destruction, to propagate the signal, and during that time, other things could start,
Right.
and I would be less efficient. And even in the sender-receiver models, it's stop tokens, which have operations on them that let you do the fan out and fan in, and so those operations all have to get called, and all the cancellation has to get done. But this is what we're shooting for. And some of the earlier versions of sender receivers, and even in the current version, because in senders receivers, the entire path for cancellation has to be known, right? Everything gets connected up as you go because it's not an on-destruction model for cancellation. And so if I've got just some lambda in my stack that's holding on to effectively a future for some current operation, that future isn't known. That future doesn't get canceled until an exception gets thrown coming from the other direction through it, which is basically serializing cancellation, because that exception isn't going to propagate down until each of the things above it is canceled, and then it comes through. And my model is a little different in that I destruct your stack bottom to top, kind of in reverse order, which is an interesting thing to live with as a developer. Eric doesn't like that, even though they've somewhat settled on similar designs. If you look at senders, receivers, and you co-await in a coroutine on a sender, and that sender gets canceled, it will destruct your coroutine without resuming it, and it's as if you had an uncatchable exception that just took that coroutine out. So it's a similar model. My cancellation is in both futures and in my current chains library is not an error, it's not an exception, and it's literally start unraveling the chain and just destruct everything up.
So you mentioned your data structure involves a lot of tuples of arbitrary types. And how do you feel about your compiler errors if those types don't line up?
It is horrible right now. So the most common error message that I get with the current library is tuple does not support this call operator. And because it's in a fold expression, it's one of the things in the chain, okay, that went wrong. So it's really, really bad. There's some potential trade-offs there. If we declared the signature that we wanted at the top of the chain, then as we append each thing, we can do a check to say, does this match? And then what's the new result of it? And then does the next thing match? And so you can do the type checking as you go. And so the compiler error you get is at the point where you're appending the item instead of at the point where you're calling it. So we have some thoughts on that. There's also a trade-off there, because that means that you can't create these constructs that are completely generic, where you could say, oh, I could take any integral type and I could do my computation and return to your result, and I can just build that thing once. Now I have to build one for ints, and I have to build one for floats, and I have to, or float is not an integral type, build it for ints and build it for long, and so on.
Because it's an interesting thought experiment. We talk about how you read code a lot more than you write code. Well, I write wrong code a lot more than I write correct code. So.
Yeah, I do too. So
maybe we should optimize for that too.
Yeah. Definitely a problem. And sender receivers, Eric has spent a lot of time on error messages, and they're still pretty horrible. But yeah. Any more questions? So I got a question for you guys before we all break. Was the talk understandable? Do you guys follow? Yeah. A little? Hanging on by your teeth, right? A little bit. Oh, thank you, Bryce. So vote of confidence there. Okay, help me out and send me some feedback.